Can you guys see me and hear me?
Yeah.
Excellent. So, crazy times. So I didn't really have anything specific for office hours. I'm actually on campus now. I just got permission to come back to campus, hoping to record a couple labs or something. But yeah, do you guys have any questions about 4A, about using Zoom, about what's going to be up?
I was wondering about number 25 on the homework. If something is rotating in a
Hold on
vertical
one second.
circle,
Chapter 25 from...
chapter 8, number 25.
Let me pull it up. 8.
I'm just wondering if there's a normal force.
Oh, no. So if you're just swinging something on a rope, no, the only time you're going to have a normal force is if you have something resting on another surface. So in the case of spinning something around, you've got tension, but there would be no normal force. Wait, let me just double check. Vertical circle, no. So it's just basically tension and gravity.
Okay. So those are the only forces acting on the object, and I should be able to use that to find...
500-gram ball moves in a vertical circle, 102 centimeter string. Speed at the bottom is that. Tension in the ball. Yep. So the only difference is at the very highest point, the tension points straight down. At the lowest point, it points straight up. Actually, let me see something. Share screen. Whiteboard. Share. So let's see how I can do this. There's a ball.
Beautiful.
And format. So this is us swinging a ball in a vertical circle. And if I look at the very highest point, basically there's just two forces. I've got tension straight down, and I've got gravity straight down. It's kind of hard with the mouse.
At
And
the
then
highest point, like on the top?
What's that?
On the top, tension is down?
So yeah, at the very highest point, tension in a rope is always a pulling force. So in this case, yeah, tension and gravity are both acting in the same direction, and the acceleration is towards the center. At the lowest point, then you've got tension acting straight up, and you've got gravity straight down. And the other difference is that the force or the acceleration is always towards the center. So at the lowest point, the acceleration is straight up.
Okay. And I was also kind of confused about number 12.
Let me see something for a second. If I stop this share, and then share screen, can you guys now see the Internet Explorer? Or,
Yeah. Yeah,
Oh,
we can
sweet.
see the PDF of the textbook on your screen.
Which problem, Jordan?
Number 12, it's just kind of weird. Like, I know that kinetic friction is a red herring because we don't want the coin to move.
So let's do this. How do I annotate? Spotlight, text eraser, format. Spotlight. That's not. So this is the problem. Problem 12?
Yes.
A 5-gram coin is placed 15 centimeters from the center of a turntable. The coin has static and kinetic coefficients of friction with the turntable surface. US is 0.8, UK is 0.5. Speeds up to 60 RPMs. Does the coin slide off? So in this case, you can figure out what the maximum value of static friction is, right? That's going to be the coefficient of static friction times the normal force. Does that part make sense? You know what? Let me see.
And then we can find the normal force because we know mg.
Yeah, in this case, let me see if I can plug this in.
And we want the acceleration to be...
Okay, sweet. Let me try something. Stop share. Share whiteboard. And let's clear all this. Okay. So yeah, I don't quite know how to draw this, but you basically, here's a side view of, this is something that's on a record player.
Uh-huh.
So yeah, you've got this mass that's sitting on this record player as the record player is rotating. And they gave you, hey there, Robert. This was number 812. And I forget, what did they gave you the number of RPMs?
Oh God, they have, 60 RPMs.
Okay, so we know that you have 60 revolutions per minute. From that, you can figure out what the speed, and they gave you the radius, right? Let me just check.
15 centimeters.
15 centimeters, 60 RPMs.
And the coin is 5 grams.
And the mass of the coin is 5 grams. Right, so if I were to sort of draw a free body diagram looking at this from the side, what I would have is I've got the normal force straight up. I've got gravity mg straight down. And the thing that's keeping this in a circular path is basically static friction. But keep in mind, static friction has a max value, which is given by the coefficient of static friction times the normal force. So I also know that this thing is moving in circular motion, so the sum of the forces has to be equal to ma, which would be, in this case, mv squared over r. So you can figure out what this mv squared over r is, and if that is greater than the maximum value static friction can have, then the coin is going to slip because static friction can't provide enough force.
Okay, so we want to find mv squared over r.
Correct.
And 60 revolutions per minute. Are we just going to like change the units on that to get like meters per second?
So yeah, so if I do 60 revolutions per minute, I know that basically in one revolution, the total distance traveled is going to be 2 pi r under one revolution. And so we've got the radius. So that's going to basically give us meters per minute. And then I know that in 1 minute, there's 60 seconds. So, you know, the minutes will cancel out, your revolutions will cancel out. This is going to give you a distance in meters. So you can basically convert 60 revolutions per minute into meters per second. And that'll be your speed for this mv squared over r.
And as long as mv squared over r is less than fs max, then the coin stays in place.
Correct. If mv squared over, so if fs max is greater than mv squared over r, then static friction will have enough force to keep it moving in a circular path. But if the maximum value of static friction was less than that, then it would slip because static friction can't supply enough force to keep it moving in a circle.
Okay, that makes sense.
All right, let me stop this share. Zoom, can I see my participants? Closed caption, chat, everyone is there. How do I see manage participants? And let me see if I unmute all. Hey, Robert, send me a little thumbs up chat. Can you see and hear me okay?
Yeah, I can hear you okay.
Oh, you can hear me, sweet. Do you have any questions about the course or Zoom or any homework questions or anything like that?
Not so much homework questions. I was just wondering, I know you've been probably crazy busy and things aren't going exactly as planned, but I was just wondering if you had test grades in course.
I have the grade. So yes and no. Everything is graded in terms of I graded every problem. I haven't added up all the grades yet. So if you send me an email, if you want to know, I've had a couple people contact me, I can email you individually.
Cool. Sounds good.
So, yeah, I
Yeah,
can let
that's all I was
people
coming
know.
down for, and just to generally check in.
Yeah, and yeah, so I'm imagining after spring break, things are going to settle down. Like just, yeah, every day I'm probably getting 200 emails from administrators and stuff. They're still figuring out what's going on. Like I think I sent the email. I came to campus at 9 o'clock this morning and everything was taped up and I had already gotten permission to come to campus and then they took it back and then they just let me come on the campus again. So
Yeah, I got the email. That sucks.
yeah, it's yeah.
Holy cow.
So all the instructors are just scrambling, trying to figure out. Like I'm trying to figure out how we're going to do labs.
Yeah, that's really weird. And it's not, I mean, even for me as a student, I'm most productive at school. So it's kind of hard for me to switch gears and be productive at home.
Oh no, same thing for everybody. And like I'm sure other people are in my situation. My daughter doesn't have school either, and so I'm trying to homeschool her and run classes and do department chair stuff. It's going to be a challenging time, and it's looking like this may be it until the end of the semester.
Yeah, it's kind of what I'm hearing
That's not
too,
the
but
case,
hopefully not.
but
Yeah.
that's what it's looking like. So people need to be prepared for that, and then I need to figure out how to collect homework online, collect labs, how to give quizzes and
Yeah.
exams, and I have no idea how that's going to work.
Okay.
So,
All right. Sounds good. I'll send you an email about the test score and everything.
okay.
Until then, I guess I'll see you on your videos.
Yeah. And just, yeah, if anything comes up, send me an email. I'm hopefully taking off tomorrow for a few days, and I'm going to just unplug because I'm going crazy. But
Cool.
I'll be back
Enjoy.
Monday. Yeah, thank you.
All right. Well, I'll talk to you later.
All right, take care, Robert.
You too.
Are you going to be sending out an email
About?
about the test scores? Like, once you have them, are you going to send them to everyone?
I
Or just
was,
a
I don't know. I mean, I can't just like send one Excel sheet to everybody. So I don't know. I was figuring I would just handle that on a case by case basis. So if you want yours, why don't you send me an email also?
Okay.
And I'll do that tonight once I get done shooting some videos and stuff like that.
Okay.
And Alex, same thing with you. If you want your celebration grade, let me know.
All right.
And Alex, do you have any homework questions, 4A questions, anything like that?
I think number 30 on the homework.
Number 30. So actually, let me just let's try this. Let's pull that up. Share screen. Oops. All right, so let's see, can I annotate? Whoa. This one, number 30?
Yeah.
3 cars are driving at 25 meters per second along the road shown in the figure below. Car B is at the bottom of the hill. Car C is at the top. Both hills have a 200-meter radius of curvature. Suppose each car suddenly brakes hard and starts to skid. What is the tangential acceleration of each? Assume the coefficient of kinetic friction is 0.1. 200-meter hill. Coefficient, suppose, what is the tangential acceleration? So we're given the speed, we're given the radius. All right, so let me stop that share and then start a whiteboard. And clear all drawings. So the big difference is one of them you're going straight, and the other one it's in a hill at the bottom, and the other one it's at the top, right?
Yeah.
So let's just draw this as a box. One case going straight, bottom of the hill, top of the hill. So in all cases, we basically have got the normal force. You've got gravity mg, and you've got the force of kinetic friction. Right, so for all three cases, those are the only three forces acting. The difference is that the normal force is going to be different in all three cases. So like in the first one over here, basically the acceleration in the y direction is 0, right? You're moving just in a
Horizontal fashion.
What's that?
Horizontally only.
Yes, there is no acceleration in the y. I'm sorry, there is no acceleration in the y direction. Here, remember, acceleration for something moving in a circular path always points towards the center. So let me change this format. So here, the acceleration is going to be v squared over r straight up. And then for this case over here, where the center of the circular path is down, the acceleration is going to be v squared over r straight down. So in essence, for this very first case, what you're going to get is the normal force is just going to be equal to mg. Second case, if I look, what I'm going to get is that acceleration is up. So I would define up as positive, which you would get as normal force minus mg equals mv squared over r. And then you could solve for the normal force. And then for this third case where you're on top of the hill, here the acceleration is down. So I would define down as positive. What you would get is mg minus the normal force equals mv squared over r. So in essence, when it's on a straightaway, the normal force is just the weight. When you are at the bottom of the hill, the normal force is going to end up being bigger than the weight. And when you're cresting the top of the hill, the normal force is going to end up being less than the weight. So in essence, what you end up doing is for each of these, you're solving the sum of the forces in the x direction equals max. The only force is the force of kinetic friction, which is mu k times the normal force equals max. And so once you know what the normal force is, you could use this to solve for the acceleration in each case.
Okay.
So the only real difference is the normal force.
All right. Gotcha.
Does that make sense?
Yeah. Thanks.
How is that to follow along with using this whiteboard?
I mean, it does its job.
Yeah. All right, if I save that, what does that do? Whiteboard saved. All right, stop share. Okay, any other questions?
Are you going to be doing lectures on Zoom or just office hours and recording?
My hope is to start doing lectures at the normal time on Zoom. That's my goal. So my goal is I don't think I'm going to try and do an hour-and-a-half lecture just on Zoom. I think that's a little much, but maybe like hour lectures. And so maybe I'll do something like from 11:30 to 12:30 on a normal time. So the answer is hopefully the lectures will be done on Zoom every day during the normal lecture time. If I can't do that for any reason, then I'll record a video and upload it. And then the labs are still figuring out, probably just going to videotape me and John doing the lab and then send out a video and give you some kind of instructions on what to do with the data. So that's the plan right now.
Okay.
Yeah, I wish I had more complete information for you, but it's sort of a work in progress.
That seems fine.
Yeah.
I don't have any other questions right now.
Okay.
I probably
Alex,
won't.
you good? Any other questions?
Yeah, I'm good.
Okay. I think I'm going to stop this then and hopefully try and shoot a video or two in lab.
All right.
All right. Well, stay healthy and stay tuned for an email from me in the not too distant future.
All right. You too.
All right. Take care, Alex. Take care, Jordan.
Bye, Joe.
Take care.
All right. Bye-bye.